Okay, so a couple more things for today. We're going to talk about how we represent these various reactions. So there are a couple different ways depending on the information that we need or the ease with which we want to look at these, okay? So everything that we've been writing so far for these precipitation reaction, we've been writing these guys as if they existed as molecules, right? So this is what we call the molecular equation. So for that, potassium chloride reaction, we had written KCl as if it existed as KCl together. We had written PbNO3 as if they existed together. And then when we went to our products, we wrote the solid together as well as the potassium nitrate. Okay, so this is what is called the molecular equation. We write these guys as if they exist as molecules, right? But the problem is that we know, especially with respect to these aqueous reactions, that they don't exist together as molecules. All of these ionic compounds instead in water exist as ions, right? This exists as K plus ions floating around and Cl minus ions floating around. This exists as Pb ions floating around as well as nitrate ions floating around. So again, when we write them like this is representative of the molecular equation. On the other hand, that isn't the real situation. So if we want to actually show what's happening in solution, the actual reality of the situation, then we can write what is called the complete ionic equation, okay? So for the complete ionic equation, any type of ionic compound, any type of strong electrolyte, any type of strong acid is going to be written as they actually exist in water, which is as ions, okay? On the other hand, any type of weak electrolytes and non-electrolytes are going to be written in their molecule form. So these are going to be things that form solids, that form liquids, that form gases in these various reactions, as well as things like weak acids, etc. So for example, I had written on the previous page the molecular equation, right? So we had our KCl, our PbNO3. So this was our molecular equation. The complete ionic equation for this reaction, we would take everything that has an AQ, right? Everything that has an AQ, and we would break it apart, dissociate it into its ion form, okay? So for this guy, KCl, if we want to write the complete ionic equation for this, we're going to break it apart into its various ions, and we're also going to take into account the stoichiometry of the reaction, right? So this 2 is distributive. So for the complete ionic equation for this, we would write 2K plus aqueous plus 2Cl minus aqueous. That's the first one. We just dissociate it into its ions, plus a Pb2 plus aqueous. And then we've got these nitrates, and that again is going to be distributive, so it goes to both of these. So this would be plus 2 NO3 minuses aqueous. Notice that I didn't write NO3 2, right, because this doesn't exist. All this really is just 2 separate NO3 guys floating around. So this is going to go to make, so now anything that exists as a solid, liquid, or gas, we're going to keep as their actual molecule form, right? So in this precipitation reactor, we made this PbCl2. In the complete ionic equation, we're going to keep that together because it does exist together, right? It's floating at the bottom of the beaker as this molecule. I guess I can't say floating. So this is PbCl2 solid, but then everything else, this aqueous thing at the end, is going to be written in its ion form. So K, 2K plus aqueous, plus, again, this is distributive, so 2 NO3 minus aqueous, okay? So that's a hassle, but this is the complete ionic equation for this reaction. So complete ionic equation. Okay, everything exists as it actually does in solution, and then you keep any type of solids, liquids, and gases in their molecule form, again, as they do in solution. Okay, so that was a hassle. Complete ionic equations are a bit of a pain to write, right? And we should note a couple things about them, right? So if we look at our complete ionic equation from the previous slide, we will note that this guy, our little potassium, is the exact same on the reactant side as it is over here on the product side, right? Same thing with nitrate. Nitrate is this NO3 over here. It is also this NO3 over here. So potassium and nitrate, these guys in this reaction don't really do anything. They don't change at all in going from the reactants to products. So we call these guys spectator ions. They are essentially just hanging around, spectating the reaction, getting in the way of what's actually really occurring, which is chlorine finding lead and making our new compound. Okay, so what will happen with respect to these spectator ions is that we can frequently remove them. Okay, so who are the spectator ions again? Here we've got potassium, nitrate, potassium nitrate. So these guys are spectating because they don't do anything. And what we can do is we can take them and we can get rid of them in our reaction, right? So we can just go, hey, you don't do anything, you don't do anything, you don't do anything, you don't do anything, and be left with the real meat and potatoes of these precipitation reactions. So this guy ends up just being 2Cl minus, aqueous plus Pb, 2 plus aqueous, going to make our PbCl2, which is a solid, and we're left with this nice little compact reaction, which is what is called the net ionic equation. Okay, so in the net ionic equation, we have removed all of the spectator ions. So all spectators are removed, and that's what it says right above it. Okay, so the net ionic equation here is again just the 2Cl minus reacting with the Pb2 plus, going to make our new molecule, our solid lead chloride. Net ionic equation. Okay, so we'll go ahead and go over a problem that's going to be utilizing some of the things that we've just learned, right? So in this question, we want to know which of these 4 solutions, so we have 4 separate solutions over here, will form a precipitate when it's mixed with an aqueous solution of sodium carbonate, right? So essentially what we have right now is we have a solution, it's completely soluble of the sodium carbonate, right? So because it's soluble, we know that we've got sodium ions floating around, and then we've also got carbonate ions floating around, right? So they're just floating around in solution. And to the solution, we're supposed to add one of these 4, right? So the first one is potassium nitrate, then we've got sodium bromide, ammonium chloride, and then copper 2 chloride, right? And with one of these, we're actually going to get a precipitate when it's mixed with our sodium carbonate solution. And the question is, well, which one, okay? So now, in thinking of this, we need to think of which type of salts are going to be formed whenever the sodium ion of our sodium carbonate mixes with the anions of these various solutions, right? Or whenever the carbonate ion of our sodium carbonate mixes with the cations of these various solutions, okay? So for the first one, when we think of what will form a precipitate with sodium, we can go ahead and just think, okay, well, I know that pretty much all sodium-containing compounds are always soluble, meaning that, when you pair sodium with any anion, it's always going to be a soluble salt, so it's never going to form a precipitate, right? So because of that, we can essentially ignore all of these guys because we know that any sodium-containing compound will always be soluble. It will never form a precipitate, a solid, okay? All right, so then we can shift our focus away from sodium because we know that nothing will form a precipitate with it, and move on to carbonate, right? And so now we're going to look at carbonate and what type of compounds it's going to form when it pairs with the cations of these various solutions, right? Now, if we go back to the solubility rules in the solubility table, we find that carbonate-containing compounds are generally insoluble, meaning that they will form a precipitate. I'm just going to abbreviate that, precipitate, except for a few different exceptions, I guess, right? So most carbonate-containing compounds are insoluble unless carbonate is paired with ammonium. And then it says the alkali metals, right, which are essentially those sodium, potassium, all of those group 1 metals, okay? So if carbonate is paired with any of these guys, then the resulting compound is soluble, meaning that it will not form precipitate. So this guy would be no precipitate, okay? So if we go over here and we look, oh, well, the first one is potassium, right? So we know if carbonate forms or makes a compound with potassium, we know it's always going to be soluble. There's no precipitate, so we can essentially ignore that first one. The second one is sodium, so we can ignore that guy. The third one is ammonium. We can ignore that guy because, again, these are our exceptions. And then finally we get to the last one where we've got copper. Copper is not part of that exception. So because of that, the compound that forms between copper and carbonate is insoluble and it will form a precipitate, right? And so this specifically is copper 2+. We know that because, again, it's bound with chlorine. Chlorine always has a -1 charge. There are 2 of them, so copper has to be copper 2+. Carbonate is also a 2-, so all we need is 1 and 1 to form our neutral or charge neutral salt. So we end up with a copper carbonate, and this guy would be a solid. All right, so the answer to this question is which solution? The answer to this is D, because copper will form a solid with the carbonate ions. Okay, so with that, I'm going to go ahead really quickly and just talk about the molecular compounds as well as the molecular equations, because we just talked about that. So if I wanted to, let's say, combine the solution of copper chloride, and I wanted to combine it with our sodium carbonate, right? So we've got sodium carbonate. We know both of these guys are soluble, so we denote them via this aqueous designation as a physical state. We could go ahead and predict the products using our double displacement method that we just did, right? So we know that sodium is going to form a compound with, we're going to just switch the partners. So we end up with the sodium chloride. And then the second thing we end up with is a copper carbonate, which we just talked about, right? So with that, right, we know that sodium chloride is going to be soluble. So it's got an aqueous designation. And then we also just talked about the fact that this copper carbonate is solid. It's got a precipitate, right? So it forms a solid. So we're going to give that the solid designation, okay? Right. So what I've written right here again is just the complete molecular equation, right? So again, we're depicting all of these guys as if they existed as molecules. The only thing that I need to do right now before I move on with this is I need to balance the equation. So right now I've got a sodium ion, it's got a 2. I've got a chloride ion here, it's also got a 2. And so because of that, over here we've only got a 1 and a 1. We're just going to put a 2 in front of this to balance it, and then we should be balanced, okay? Okay, so then from there, I'm going to go ahead and write out the complete ionic equation, right, where everything essentially is going to be as it is in solution, right? So anything that's aqueous is going to break apart into its 2 ions. So here we're going to have a copper 2+ ion floating around. And then again, we always want to write Cl2, but that's not actually what's happening, right? All that is telling us is that there are 2 Cl- floating around. Then we move on to the same thing over here. We've got a 2 sodium+ ions floating around. And then a carbonate, just one of those, that's a 2- floating around. It's going to go to form 2 of these guys and 2 of these guys. So 2 sodium ions plus, I'll go ahead and zoom out a little bit, 2 chloride ions. And I start to spread too much. And then finally we come to the thing that is an actual compound, that is an actual molecule. And so this is our solid, our copper carbonate. So we're going to go ahead and just write that as CO3. solid, right? Anything that's a solid, a liquid, or a gas, we keep as its actual molecular format, okay? So that's the complete ionic equation. From there, of course, what we really want to write is the net ionic equation because it's much easier. And again, it's like the meat and potatoes of what's really happening. So we'll note that our chlorines here, our sodiums here, they're the exact same thing on the product side as they are on the reactants, right? So we can go ahead and get rid of those. These guys are our spectator ions. Spectator ions. And so then in the net ionic equation, we're just going to write what actually does any type of chemistry. So we have copper, 2+, aqueous, that's coming from here. We've got carbonate, CO3 or 2-, aqueous, and they're going to form our one solid, which is copper carbonate, which is a solid. Okay, so that's just another, like, okay, this was, no, it wasn't necessarily the problem, but again, it gives you another example of writing out the molecular, the complete ionic, and the net ionic equations.